Good morning, everyone. My name is Lesor, and today I'll be speaking about an application that most of us know of or have used at least once in our life, Shazam. So picture this. You You at a club or at a coffee shop, a song starts playing. You know you've heard it somewhere, but you're not quite sure of the name of the song or the artist or even the album that it's from. In comes Shazam. So Shazam basically gives you the power to press a button and then it will listen to the song, it will analyze it, and then basically identify the song for you. Here's a brief journey of Shazam. So Shazam started off in 2000. That's when the company started. It started as a call-in service. So you basically had to dial a number. Bear in mind, this is before smartphones. So you had to dial a number, um, place your phone next to the audio, and then it would listen and it would send you a text of basically what the song title is, the artist, and the album that it is from. And then in 2008, Shazam launches its app on the App Store and later on Google. In 2018, Apple acquires Shazam for 400 million, and today Shazam processes over 70 billion queries. So in saying all that, what is Shazam? So according to this guy, Avery Wang, who's one of the co-founders of Shazam and currently works at Apple as a principal research scientist, he wrote a paper basically titled An Industrial Strength Audio Search Algorithm. And in that paper, he describes Shazam as a audio search engine, which makes sense, right? I hope we all know what search engines are. So prime example would be Google. So how Shazam basically works, just a quick overview. You'd get an audio, and then that audio basically goes through an algorithm, and then that algorithm produces hashes. Hashes are basically a data set that can relate back to the song that's playing. So how does it do that? So it goes through three main steps. I used real life scenarios to try and make it easier for everyone to understand. The first step is the constellation maps, or what I like to call stargazing for music. It creates something called a spectrogram. For those who don't know what a spectrogram is, it's basically a visual map of sound frequencies over time with intensity. So that what you see here, that would be a spectrogram. And then it finds the strongest sound. The strongest sound usually looks like a peak. So the peak sound in the song, it tries to find that. A good analogy would be like you out at night, you look up into the stars, and then you basically identify the brightest stars. And then after that, it creates a constellation map. So these peaks are then connected into a unique constellation-like pattern to identify the song. So same analogy, the way you can look up into the stars and then basically identify Orion's. A question that you might be asking is, what about? So Shazam basically ignores all that sound. For example, you're in a room of people, crowded people, but you can still distinctly identify your friend's voice. So that's what Shazam does. So now we have a constellation. In essence, you can basically identify the song, but we run into a problem. What if a song is playing, and then you try and find out what the song is halfway through the song? You won't be able to do that. So in comes fingerprint hashing. So what fingerprint hashing basically does is it takes an anchor point and then it tries to map it to a target. So instead of saying this peak happened at 1 second, we basically now saying that this peak happened, or this peak comes 5 seconds after this anchor point. And thus solving the issue of time called relative timing. So now that we have the timing, how do I get the song? So Shazam basically converts your sound into fingerprint hashes, and then it does a search for matches in the database. And then after that, it does a time-based scatter plot, which is basically matching fingerprints are plotted on one axis for sample time and one for database time. So for example, not sure if you can see that diagram there. So the y-axis would be the sample or the song that's currently playing, and then the x-axis will basically be the database song. And then it tries to match it, and then it creates something called a diagonal line pattern. So a diagonal line pattern, it basically means that the sample and track are aligned or are in sync. The efficiency of this is that Shazam only needs 1 to 2% of the audio to successfully identify the track. So yes, it's not magic, it's just math. So the good thing about this, it works over a ton of noise. So for example, my analogy where you're in a very loud environment and it is able to pick up the peaks, it's very fast. It's able to detect multiple songs. It's able to distinguish versions. So if a remix or the original is played. So there are multiple real world uses of this. It's not just for finding songs. So it's also used in copyright monitoring, ad tracking, archiving, and indexing. It's a long animation. So the next time you use Shazam, just remember, it's not just guessing. It's doing some crazy fast maths in the background, and it's building a constellation map. It's then fingerprinting sound to like a detective, and it's finding matches in a sea of millions of songs. All this while you trying to figure out or trying to remember the lyrics. So technology like this reminds us that the line between science and magic is often just great engineering. Thank you.